So, essentially all intermolecular forces are the result of partial positives being attracted to partial negatives. This is true even if the molecule itself is nonpolar. Whether it's polar or nonpolar, there will still exist these partial positives and partial negatives in molecules that will be attracted to one another. The old saying, opposites attract, is pertinent here. So now a dipole refers to when one side of a molecule is positive and the other side of a molecule is more negative. And so really the difference between the different intermolecular forces comes down to whether or not the strength of this dipole is larger or smaller. And it will be larger or smaller based on what the dipole is caused from. So we'll look into that. So there are three main types of intermolecular forces. There's London dispersion forces, there's dipole-dipole forces, and hydrogen bonding. Now, as it says, the London dispersion forces are caused by weak temporary dipoles. So what you end up having is these molecules crashing together. Normally they're not polar, but after they crash together, you'll have a disturbance. It's kind of like if you have a glass of water or a tub of water. If you have a glass of water and you bump it, what happens to the water? Yeah, it shifts around, kind of waves, right? And the same thing is true with these electrons. These electrons are spinning around in clouds very quickly. And when they smash into each other, that's going to cause a disturbance in the cloud. Now, it may not be much of a disturbance, but it's still a disturbance. And that disturbance will cause some of the electrons to be closer to one side than they will be to the other. So, but these disturbances, these dipoles that result from these nonpolar molecules crashing into each other, they don't last very long because the molecules are nonpolar to begin with. So these dipoles, they kind of like stabilize pretty quickly. Just like if you bump a glass of water, the water's going to like shake a little bit, but then it's going to settle. So these are weak temporary dipoles. Dipole-dipole forces are a little bit stronger. So these are from polar molecules. Any polar molecule is going to have dipole-dipole forces. Now, a polar molecule will also have London dispersion forces, because dispersion forces are due to these fluctuating dipoles, these fluctuating areas of more or less concentrated charge. And the larger a molecule is, the more London dispersion forces they're going to have. So London dispersion forces can be very significant. Individually, each occurrence is pretty weak. But if you have a very large molecule, these can actually be very significant. Like if you have, for example, like if you have a tug of war, if it's just you versus like, J.J. Watt or somebody, somebody like a football player, offensive lineman or something, you're probably going to lose the tug of war, right? But if you got like, 20 of us versus just one of them, well, we're probably going to win, right? Because the combined force of 20 of us is going to be greater than his force, even as strong as he is. So, same thing with London dispersion forces. They can actually be very significant with larger molecules. Now, dipole-dipole forces caused by polar molecules, because these are permanent, these are always stronger per incidence. And they don't go away, they don't fluctuate, they are permanent dipoles. And then hydrogen bonding is really just an extreme case of dipole-dipole forces. Essentially, what happens is you get almost what are referred to as, I guess you could think of them as almost like pseudo-bonds. They're not quite bonds, but they're almost as strong. In fact, biology considers hydrogen bonding to actually be bonds. Whereas in chemistry, we don't consider them to be bonds, we consider them to be intermolecular forces. So it's the lone pairs that are on a highly electronegative atom, such as nitrogen, oxygen, or fluorine. And they're attracted to the hydrogens that are bonded to highly electronegative atoms. So I'll give you an example. So you can't have hydrogen bonding with one molecule. this is not hydrogen bonding. That's not a hydrogen bond, okay? Hydrogen bonding is when you have two or more of these molecules, and it's the interaction between, this lone pair here on this very huge partial negative and this attraction to this partial positive on this hydrogen. And because this is a lone pair here, it almost acts as if it was starting to bond with the hydrogen. And that's why the hydrogen bonding is so much more powerful than, say, simply like a dipole-dipole. If it was just charges, well, that wouldn't be quite enough, right? If it was just charges, it's not going to be the same as like a covalent bond. But because you have this lone pair of electrons that wants to kind of attach to this hydrogen, that's what gives hydrogen bonding its particular strength. So hydrogen bonding, the key thing is that it can only happen if you have a molecule with HN, HO, or HF bonds. Does that make sense? Cool. So London dispersion. Yes.
Sorry. But a quick question, in any problem where it's asking us what kind of bond it is, and
Yeah.
it has HN and it just lists it as one time, would we classify that as hydrogen bonding because you would assume that it's more than...
Yes, you would assume that it was, you would assume that it would be hydrogen bonding just because the molecule has HN or HF or HO. Okay. So now, hello. So now we'll take a look at London dispersion forces a little bit more. So there are a couple different causes for London dispersion forces. One is the random motion of electrons in a molecule. So electrons at any given point could, just by rapidly moving around the molecule, could be at any given point more concentrated on one side of the one side of the atom than the other. That's going to cause a dipole. Or rather, that's going to cause London dispersion forces. That's going to cause those partial positives and partial negatives. And then, secondly, you can have induced dipoles due to either the collision of molecules when they crash together, just like bumping a glass of water, or if you have electrostatic forces between the molecules that come close to each other. So, for example, let's say these two atoms don't actually crash into each other, okay? Let's say they actually just come close to each other. Well, if the electrons are closer to one side than the other, and you have a partial positive on this side and a partial negative on this side, even if it's just close to another atom, the fact that there's a partial positive here is going to attract the electrons in another atom over here. And that's going to pull these electrons over to this side, which is going to cause a dipole in a neighboring atom. So they don't actually have to crash to cause a disturbance, to cause a partial negative and partial positive to be on different sides. In this case, all it has to do is come close to each other. So if they either crash or if they just come close to each other, you can get these small partial positives and partial negatives. So London dispersion forces are essentially proportional to the polarizability of a molecule. So what does that mean? It's kind of a fancy word. It's like to what degree can you move electrons to one side of the molecule or the other? Well, if a molecule is larger, in other words, if the atom has more electrons, if it's a big atom like bromine or iodine, the more electrons there are, the more polarizable it is because there's more of a likelihood that those electrons could be shifted to one side or the other. Also, the longer a molecule is, if you have a 20 carbon chain, or even like an 8 carbon chain, like octane, gasoline. So gasoline, 8 carbons with hydrogens attached to them, 8 carbons in a chain, it's actually a pretty long molecule. And it ends up being a liquid, whereas smaller hydrocarbons like methane, just carbon with 4 hydrogens bonded to it, that's going to end up just being a gas. So the longer it is and the heavier it is, the greater its polarizability. Longer and heavier, greater polarizability. So, one quick note here. If I have, say, for example, butane, and so there's these hydrogens here, and if I have a molecule that's an isomer, which essentially means it has the same number of atoms and the same kind of atoms, but they're just connected in different ways, it's called an isomer. Now these both have 4 carbons and 10 hydrogens. Which one of these molecules would have greater intermolecular forces? Which one of these molecules would have greater London dispersion forces? Yeah, because this one is longer, it's easier to make this more polarized. It's easier to polarize this. Electrons can be pushed more to one side or the other. Because this is more condensed, the carbons are kind of in a more condensed structure, they're closer together. The electrons will tend to pool around the same area, and they won't have as much opportunity to get tangled around, kind of like a noodle. They won't get tangled around each other, and the electrons won't get pulled over to one side or the other as easily. Okay, cool. So then, any questions on London dispersion forces?
Can you repeat this one more time, please?
Sure. If you have 2 molecules that have the same number of each type of atom, same number of carbons, same number of hydrogens, everything else, the one that's longer is going to have greater intermolecular forces. The one that's longer is going to have greater intermolecular forces. The one that's more branched is going to have weaker intermolecular forces.
This is not until the 6th one.
This isn't for your class. You're taking 1406, right? Yeah, this is for 1412. The 1406 one is going to be later at 7 o'clock. Sorry. Okay. Any other questions? We good? Okay. Let's take a look at crude oil. So this kind of gives you an idea. So when crude oil is taken from the ground, it's separated into all the different types of substances that are present. And they're all carbon-based substances from the decay of plant and animal matter. So the really, really heavy stuff is like 70 carbons long or longer. That's like tar, or like tar and the stuff they use for roads and roofs and things like that. It's that really thick, sludgy stuff. That's what is on the very bottom here. However, at 600 degrees Celsius, essentially when they heat the crude oil in the column, and the lightest ones go straight to the top. And the lightest ones are methane through butane. They come out as gases at the very top at 20 degrees Celsius. The heavier stuff, like it says naphtha, but it actually can also include gasoline, would be in that third one, C5 to C10. And essentially, the further down you go, you get into these thicker and thicker oils and such. Whereas the lighter ones are very liquidy, like gasoline, and they evaporate real quickly. So essentially, one of the things you notice is that the longer these carbons are, the boiling point is much higher, right? So the longer these carbons are, the longer these carbon chains are, the larger the boiling point. The boiling points get actually considerably larger than something that has hydrogen bonding, like water, for example. And that goes back to what we were saying before, that longer molecules and heavier molecules have greater intermolecular forces. And greater intermolecular forces means they're harder to separate, which means they need higher boiling points. So, let's do a couple of practice problems. So, of these two, which one would have the greater intermolecular forces? Carbon tetrachloride or methane? CCl4. Yeah, because chlorine is a lot heavier than hydrogen, right? The mass of chlorine on the periodic table is about 35.45, whereas hydrogen is only 1.01. It also has 17 electrons, whereas hydrogen only has 1. So they're much bigger atoms and have much more polarizability. What about this one, H2TE or H2S? Do I need to pull up a periodic table? Do you have a periodic table? Should be at the front of the book.
I knew this one in.
So tellurium actually, I think, is a couple down from sulfur.
And then, okay, so until the H2.
Yeah. Heavier atoms, larger atoms, greater intermolecular forces. And then between these two, which one would have the greatest? The pentane, because it's longer, right? Same mass, longer. Okay. So let's take a look at dipole-dipole forces. So we already talked a bit about it. They have permanent dipoles. Because one atom is more electronegative than the other, it's going to pull electrons closer to it, and it's going to end up with a much larger electron cloud than the other one's going to have a smaller electron cloud. And so this is always going to be partially negative because of the greater amount of electrons on that side. There's always going to be partially positive because less electrons on that side. And so negative is going to be attracted to positive, and you have dipole-dipole forces. And it's called it's kind of weird to say the word dipole twice. You say, why can't we just call them dipole forces? Why do we have to call them dipole-dipole forces? Well, it's because it's not a force between one dipole, it's a force between two dipoles. This dipole and this dipole. So that's why we say it's a dipole-dipole force. Otherwise, there's also something known as ion dipole forces, and that's when you have actually a charged ion attracted to a dipole. And so those aren't quite the same thing. But we do want to emphasize dipole-dipole forces.
Question?
Yes.
Are you recording? Am I in the way?
We are recording, but your head is not in the way.
Okay.
Yeah. Sorry. So I'm recording this for all the people who can't be here. I'm trying to ideally I would have a cameraman to kind of move the camera around from there to there, but we'll have to work on that until we get more work-study students. I'm making it a point to try to avoid capturing anybody's face because not everybody wants to be on video.
Yeah.
So I'm making sure that I'm not catching anybody's face when I'm recording. So I hope you all don't mind. If anybody has a problem with me recording, I can actually stop it though. Okay. All right. Now hydrogen bonding. So this is interesting. So like I said, it's a special case of dipole-dipole forces. The difference in electronegativity is extreme, and there's also a lone pair of electrons that we were talking about before. Lone pair of electrons on the highly electronegative atom that attracts and kind of forms almost like a partial bond with the hydrogen. So without dipole-dipole forces, you would expect, without hydrogen bonding, you would expect this pattern for this one here to do the same thing that this one here does. So notice SNH4 is a non-polar molecule, okay? H2TE is a polar molecule. As a polar molecule, it has a higher boiling point than SNH4. They have comparable weights. They're about the same weight, close to. But this one has a higher boiling point because it's polar. So that's the difference between polar and non-polar. Polar, non-polar. Polar, non-polar. However, notice that they both go down like this. And that is because, what's the difference between this one and this one? Well, they're both polar, so it can't be that, right? What's the difference between this and this? Why does this have a higher boiling point?
Because S is more electronegative.
actually it's less electronegative than S. So it's actually a smaller dipole-dipole force. So why is it greater in the boiling point? Which means
molar mass.
molar mass. Because of London dispersion forces. Remember I said these are additive. You have the London dispersion forces and you have the dipole-dipole forces. So any molecule that's polar not only has London dispersion forces, it also has, not only has dipole-dipole forces, it also has London dispersion forces. Pretty much any molecule has London dispersion forces. But the heavier the molecule is, the more important they become. So yeah, even though this has a stronger dipole-dipole force, this actually has greater London dispersion forces, and so that more than compensates for the fact that it's slightly weaker on the dipole-dipole front. So you kind of got to take both into account. Now, these guys are nonpolar, so all they have is London dispersion forces. And so as they get heavier, you see this notable increase. And you'll also notice something kind of interesting. The difference between being polar and not polar, dipole-dipole versus just London dispersion forces, pretty significant, right? Whereas the difference between having London dispersion forces added on top of polar one, not as big of a difference. You see what I'm saying? It's like this is only like this much difference, whereas between polar. So that kind of emphasizes the fact that the dipole-dipole forces are a pretty big deal. There's a big difference between, they're usually much stronger than London dispersion forces. However, if you notice a big difference in weight, a big difference in weight can actually be more dramatic than the difference between polar and non-polar.
Are all of those examples of hydrogen bonding?
No, none of them are.
Okay.
Except for water.
Okay.
And that's where you notice this very strange aberration. Normally you would have expected it to go down like this one, but because of hydrogen bonding, because of that unique character of being able to form that kind of partial bond, because of the extreme electronegativity of oxygen, you notice that the actual intermolecular forces for water skyrocket. So hydrogen bonding it's really kind of a special case. It's more than just simply a stronger version of dipole-dipole forces. It actually forms a sort of pseudo-partial bond, and that gets an extremely increased value for intermolecular forces. Does that make sense? Cool. All right. So like I said, with hydrogen bonding, there's only three different atoms that can bond, that when they're bonded to hydrogen can allow you to have hydrogen bonding, and that's NH, OH, or FH. So nitrogen, oxygen, or fluorine. Or in other words, hydrogen bonding is fun. Kind of. Cool. Hydrogen bonding is fun.
I was literally going to look at my notes to remember each one, but that's better.
I know it's kind of ridiculous. It doesn't actually kind of work, but maybe it does kind of do it. All right. So hydrogen bonding is what causes ice to be lighter than water. And if ice was not lighter than water, the oceans would never thaw. They would be frozen underneath. You'd have no life down there. It would probably kill a lot of sea life. It would actually maybe have prevented life from even developing on this planet in the first place, except other than like maybe bacteria or whatever. So it's very important that hydrogen bonding exists. It's also what allows trees to, along with capillary action, allows trees to pull water up and nutrients up, plants to pull water and nutrients up. It's such an important part of so many factors in biology, which you'll learn in your biology classes. It's also a key factor of what allows for the DNA to unzip and zip back up. It's the hydrogen bonding interactions between the nucleotide bases. So hydrogen bonding is crucial to many aspects of life and biology, etc. So this actually shows the different like base pair hydrogen bonding interactions. The NH here, the lone pair of electrons here being attracted to the H, the NH here, and the lone pair of electrons in this oxygen being attracted there. So get a lot of that. So now ion dipole forces are interesting. They are the strongest of the intermolecular attractions. So really the only time you have ion dipole forces is when you have ionic substances that are dissolved in a polar solvent, and usually a polar solvent with hydrogen bonding. So water, alcohol, something like that. That's when you're going to have ion dipole forces. And essentially what happens is the ionic compounds are broken up into their separated ions, and those charges, like the negative charge, will attract all the partial positives from polar solvent, and the positive charge will attract all the partial negatives from the polar solvent, and so you end up getting these complexes around the ions. Now these are actually quite strong, and some argue that this is an intermolecular force. Some argue that it's too strong to be considered an intermolecular force. You don't have to worry about that. Suffice it to say that these are even stronger than hydrogen bonding. Even stronger than hydrogen bonding. And so some people want to try to call them like a partial covalent bond. They want to call them bonds, but you don't have to worry about that. You can just think of them as an intermolecular force if you want.
Inter? You
So,
said inter or intra?
Inter. Yeah, intramolecular forces would be referred to as bonds. So if you're looking at something like this, a covalent bond between carbons, that's within the molecule. So that could be considered, if you want, an intramolecular force. Intermolecular forces, which is what we're talking about here, is attractions between different molecules, not between atoms within the same molecule. Okay. So they have this very cool flow chart that I'm very proud of, and essentially it's going to kind of give you an idea of what you actually have here. All of these, in a certain sense, can be considered under the auspices of intermolecular forces. Although technically speaking, ionic bonding is typically classified as bonds. But every single one of these is related to partial positives being attracted to partial negatives. So, if there's no ions involved, and the molecules are nonpolar, you have London dispersion forces, the weakest. Weak partial positives attracted to weak partial negatives. If there are polar molecules but no ions, and there's no hydrogen bonding, then you have dipole-dipole forces. Permanent partial positives and partial negatives, but relatively weak still, not super strong. If you have HN, or HN, HO, or HF atoms, and you have hydrogen bonding, then you have very strong partial positives and partial negatives. However, if there are ions involved, and you also have a polar solvent, then you have ion dipole forces. And this is even stronger partial positive. Actually, it's a full positive or a full negative with a partial positive and a partial negative. So there's a strong electrostatic attraction between them. And then lastly, you have ionic bonding, which is a full positive attracted to a full negative. And that's the strongest electrostatic attractions. So every single one of these are electrostatic attractions. Positives attracted to negatives. The weakest positive, weakest negatives, partial and temporary. A little bit stronger, quite a bit stronger. Full positive, partial negative, or full negative and partial positive, and then full positive, full negative. So it gets stronger as you go to the side. And these three are the ones that are typically considered your intermolecular forces. This is sometimes also included in that. Any questions? Yes?
How can I distinguish between molecule or ion? How can I?
Well, an ion, you can tell if it's going to be an ion if it's an ionic compound. So if you remember from last semester, ionic compounds are when you have metals and nonmetals, like potassium bromide or sodium chloride, NaCl. So when you have those type of compounds, you have ions. A molecule is not going to, it's going to be composed of nonmetals only. So CO2 or NH3 or H2O. Okay, so polarity is, this is the thing that kicks everybody, because polarity is probably one of the trickier concepts in chemistry. For a two-atom molecule, it's actually pretty simple. If the atoms are not the same, like if you have an H atom and a fluorine atom, it's going to be polar, right? Because there's different electronegativities. But if the atoms are the same, there's no difference in electronegativity, it's going to be nonpolar. So that's for a two-atom molecule. In that case, it's pretty easy. But when you're dealing with more than two-atom, I'm going to skip this part real quick. This is basically just emphasizing the fact that if the atoms are different, they're going to have different electronegativities, and therefore they're going to be polar because one's going to pull in the electrons more than the other. But for larger molecules, you actually have to look at what's referred to as the net dipole moment, and a lot of this comes down to symmetry. So, in essence, if all the atoms bonded to the central atom are the same, and there's no lone pairs, it's going to be nonpolar. Because if this is pulling this way, and this is pulling this way, and this is pulling this way, and this is pulling this way, they're all basically in geometrically opposite directions and with equal strength. It's like a tug of war, but everybody's equal strength. Nobody's going to win, right? So the electrons are going to be equally balanced, and you're going to end up having a nonpolar molecule. However, if not all of the people on the tug of war are pulling with equal strength, if one of them perhaps is a little bit stronger, like in this case you have chlorine here, which is more electronegative, then you're going to have electrons tending to flow towards the most electronegative atom. This is going to have a partial negative around it, whereas these guys down here will have partial positive, and you'll end up with a polar molecule. So, as you can see, there's a certain asymmetry here, right? It's not balanced. Whereas here, there's kind of like almost like a symmetry, like no matter how you cut it, it's going to be pretty much the same on one side versus the other, right? And the same thing with this one. So this is a trigonal planar molecule. So, but net dipole moments can be kind of tricky. So I developed a list of 3 rules for quickly and easily determining whether or not a molecule would be polar or nonpolar. And, well, I guess first let's look at a few examples. So, carbon dioxide, you can see there's oxygen on this side, oxygen on this side. It's linear, because you have to take into account molecular geometry when you're looking at these. If you're doing the net dipole moment type thing. Now in this case, oxygen's on both sides, so it ends up being what? Polar or nonpolar? Nonpolar. It's, yeah, there's a symmetry there. Carbon tetrafluoride, polar or nonpolar? Nonpolar. There's a symmetry there. It's pulling with equal strength on each side. What about water? Polar. And you can clearly see in this electron diagram here, the blue represents an area of very low electron density, and the red, very high electron density. One side is much more positive, and the other side is much more negative. So if you're just looking at a Lewis structure, this is probably the safest way to determine whether or not something is polar. If a molecule has one pair of electrons on the central atom, the molecule is polar, no matter what. So if you see something like this, that's going to be polar. Actually, even if you see something like this, now this is a little goofy because notice that all of these atoms are oxygen. This is ozone. All of these atoms are oxygen, so each one of them should have equal electronegativities. However, what you notice is that even though they have the same electronegativity, there's this lone pair on the central atom. And this actually ends up being a bent molecule. You have this cloud of electrons up here, and you have a bent molecule here. And what ends up happening here, you get a disequilibrium of charge, and this ends up being a polar molecule. So you can actually have polar molecules with non-polar bonds. And you can also have non-polar molecules with polar bonds. So that's why I kind of put together this over here, these rules to help make it a little bit easier. So if there's a pair of electrons in the central atom, the molecule is polar no matter what. If there is not a pair of electrons in the central atom, then, and all the atoms bonded to the central atom are the same, then the molecule is going to be nonpolar. So, okay, so this is the first. So the first rule is lone pair on the central atom, polar. If it has two or more lone pairs, it will be polar unless those lone pairs are in geometrically opposite positions. So let me show you a couple examples of that. Because you have seen this come up before last semester. You have seen this come up before. So let's say you had something like this. XeF2, xenon difluoride. Okay. You have 3 lone pairs on xenon. So, if you look at this, you see that these are in geometrically opposite positions. With 5 electron domains, this is trigonal bipyramidal. So it's basically like trigonal planar, but with a rod slammed through the top of it. Okay? Because these are in geometrically opposite positions, their effect cancels each other out, and you only have to look at the dipole moment due to fluorine. Once again, you see that there's a sort of symmetry here, right? If it's symmetrical, it's going to tend to be nonpolar. Now, there's no way to tell just by looking at XeF2 if that's going to be polar or nonpolar. You kind of have to draw the Lewis structure. Okay. Now, because in the same way, if you had something like, OCl2, that would actually end up being polar. And so this and this look awfully similar. 1 atom in the center and then 2 atoms attached to it, right? So the only way to tell whether or not something is polar or nonpolar sometimes is to draw the Lewis structure. But from the Lewis structure, you can then see whether or not it's going to be polar or nonpolar.
This is nonpolar.
That's going to be nonpolar. So if there's 2 or more lone pairs, they're going to be polar unless they're in opposite positions. The other case that you can have here, and just because this is another classic one that professors like to throw on exams and quizzes, XeF4. So this is XeF2, and this is going to be XeF4. And in this case, there's a lone pair on the top and a lone pair on the bottom. And this is what's referred to as square planar. 6 electron domains, but 2 of them are lone pairs. So you have this kind of square planar structure here. Notice that the lone pairs are in opposite positions. One's going up, one's going down. So that's actually going to make this nonpolar as well. But even though I've shown you these exceptions, the vast majority of the time, anytime you see a lone pair, it usually means it's going to be polar. So, for example, you have PCl3. Polar or nonpolar? Polar. If you have H2S, polar or nonpolar? Polar. You have to remember, Lewis structure doesn't show three-dimensional. This actually looks like this, right? Tetrahedral, which means those two lone pairs are always going to be on one side more than the other. So remember, unless it's one of these special cases, trigonal bipyramidal or square planar, lone pairs means it's going to be polar. Vast majority of the time, electrons on the central atom is polar. Now, what if there's no electrons in the central atom? If there's no electrons on the central atom, no lone pairs that is, and the atoms bonded to the central atom are the same, then it's going to be nonpolar. So that, what are some examples of that? What are some examples of that? Let's take a look. So if you have CH4, no lone pairs, and all the atoms in the central atom are the same, right? So that's going to be nonpolar. What about if we have some polar bonds here, like CCl? Polar or nonpolar? Nonpolar. Because all the atoms are the same, so they're all pulling in the same direction, so this is going to still be nonpolar. What about if I have something like this? Polar, why?
Because it have different atom attached to the central atom.
All the atoms bonded to the central atom are not the same anymore. One of them is oxygen, which is oxygen. And actually this one has an OH, so this would actually technically be hydrogen bonding. Very good. Now, just in case anybody has forgotten how to draw Lewis structures, we can go over that a little bit in a little bit when we go over some practice problems. But for now, does this make sense? Okay, cool. What?
So what time does this last?
What?
Oh, so what time does this
We started a little bit late, so we'll probably go just a little bit after 6.
Okay.
So list all of the intermolecular forces acting on 2 phosphorus trichloride molecules. So in a question like this, the first thing you'd want to do is identify what the formula of the molecule is. So what is phosphorus trichloride? What's the formula? Phosphorus trichloride. What would the chemical formula for that be?
FCl3.
P what?
FCl3.
PCl3.
PCl3.
Oh, I said.
Yeah.
I'm thinking in Spanish.
Yeah, that's good. So PCl3 would be the formula of phosphorus trichloride. So now, from there, we want to draw the Lewis structure. Well, the first thing you want to do in drawing the Lewis structure is identify how many valence electrons you have. How many valence electrons does phosphorus have?
5.
5. And you can tell that from its position in the periodic table. Valence electrons are the outermost S and P electrons. If I was to draw a periodic table, I think, yeah. Okay. So, 1, 1, 2, 3, 4, 5, 6. Okay. So your S block and your P block, here's your S, here's your P. We don't care about the D block because they don't have valence electrons. Phosphorus is, here's nitrogen, but here's phosphorus right underneath it. And then you have O, F, and Ne, right? And P, S, Cl, C, Si, B, and okay. So, phosphorus, 2 plus 3, 5 valence electrons. It's also the 5th column of the representative elements. Remember the S and P block elements are your representative elements. 5th column, 5 valence electrons. So 5 valence electrons from phosphorus plus chlorine has how many valence electrons?
7.
How many?
7.
7. So there's 3 chlorines, 7. So 3 times 7 is 21, plus 5 is 26. So we have 26 total valence electrons that we can work with. The first thing we do after this is to draw what I like to call a skeleton structure. Show how the atoms are connected. Usually the first atom listed is your central atom. So it's P, and it's connected to 3 chlorines. Oh, now, before I start throwing on electrons, each line here is a bond, which means it's a shared pair of electrons. So how many electrons have I used up so far?
6.
6. So I take away 6, I have 20 electrons left. 20 electrons left. I'm going to place my remaining electrons in pairs, not one by one. Must be in pairs. So 2 by 2, I'm going to add 20 electrons here until I can't add any more. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so essentially what I do is I add electrons to the most electronegative elements first. And chlorine is more electronegative than phosphorus, because do you all remember what the trend for electronegativity is? Yep. Yeah, up and to the right. Out closer to fluorine, more electronegative. So chlorine is more electronegative than phosphorus. I put the electrons out here first. And I've placed all my 20. Now, I don't want any more than 8, right? 8 is the octet rule, that's the ideal. I can have more than 8 if I absolutely need to, but only for elements that are in the 3rd period or below. I can't do it with the 2nd period. So, but in this case I didn't need to. They all have 8, they're all happy. Now if one was short, then I might have to make a double bond, but in this case I don't. So now I see that there are lone pairs in the central atom, right? So what type of molecule is this? Polar or non-polar?
Polar.
Polar. So what type of intermolecular forces would it have? What'd you say? You were saying it. What? It does have London dispersion forces. Does it have anything else? It also has dipole-dipole. Remember, everything has London dispersion forces. So if you have to guess, you're safe guessing London dispersion forces. But this one also has dipole-dipole forces, and that's important. So each one of these would have dipole-dipole and London dispersion forces. So as a strategy for solving this type of problem, figure out the formula, draw the Lewis structure, figure out the molecular geometry. Although, truthfully speaking, if you use those rules that I taught you, you don't really need the molecular geometry. You could simply recognize one lone pair, it's automatically going to be polar. And then if it's polar, that means dipole-dipole. So it says, which of the following molecules have only London dispersion forces?
XCF4.
I'm sorry?
XCF4.
XCF4, we've already done that one, right? That was non-polar. So that would only have London dispersion forces.
What, NH3?
So NH3, let's see.
So hydrogen bond.
A hydrogen bonding, yeah. Anytime you see NH, OH, or FH, hydrogen bonding. But if you wanted to draw the Lewis structure for NH3, nitrogen has how many valence electrons?
Five.
5. And hydrogen has how many? 1. And there are 3 hydrogens, so 3 times 1 is 3, plus 5 is 8. I draw my skeleton structure. H, H, H. How many valence electrons have I used up?
6.
6. 8 minus 6 is going to give me 2 left. I only have 2 valence electrons left. Does hydrogen want any more electrons? So I have to put them on nitrogen. So clearly it's at least going to be polar, right? Because it has, but the fact that it has NH bonds automatically means hydrogen bonding. Now, what about the CH2Cl2? Would that be just London dispersion forces, or would that have any other type of intermolecular forces?
Is there a quick way to like know that in your brain?
We have to draw the Lewis structure for that one, don't we?
What?
I said we have to draw the Lewis structure for that one, don't we?
It would help if you draw the Lewis structure. You don't absolutely need to.
I would.
Because in this case, okay, so carbon, when you have carbon listed first, it's the central atom. That means all the other atoms are connected to the carbon, right?
Okay.
So if I was to draw the skeleton structure for this, it would be C, H, Cl, H, Cl, or I could put the Cl here and here. Now in this case, are all the atoms bonded with the central atom the same?
No.
So that means it's
Polar.
polar. Because remember, this is actually like this, right? It's not actually like a flat square like this. The chlorine is actually not on the opposite side of the other chlorine. So this is going to be polar. Anytime the atoms are not the same, it's going to tend to be polar. So this is polar. And if it's polar, does it have more than London dispersion forces? Does that? What about BH3? This is one of those exceptions that professors like to throw at you because they're being. You would think it would be polar because it's similar to NH3, right? But boron is actually an exception to the octet rule. It only tends to like to form 3 bonds. And because it only tends to form 3 bonds, it has no lone pairs on the central atom. And all the atoms bonded to it are the same, which makes it non-polar. So the last 2, C and D, are going to be the ones with only London dispersion forces. And O3, of course, we already looked at that one over there. That one, yeah. So now, polarity of organic compounds. So this is another interesting factor. If you have to measure between levels of polarity, in general for organic compounds are compounds that have carbon and hydrogen in them. So for organic compounds, the more oxygens you have and the fewer carbons you have, the more polar it is. So the more bonds to oxygen, or the more oxygens you have, and the fewer carbons you have, the more polar it is. So I have an alcohol with 3 carbons, I have an alcohol with 2 carbons. Which one's more polar? The one with 2 carbons. I have an alcohol, a 2-carbon alcohol and a 2-carbon carboxylic acid, which has 2 oxygens. Same number of carbons, but this one has 2 oxygens. This is going to be more polar. So that's kind of sort of a general rule when dealing with organic compounds. The more oxygens or nitrogens, the more CO or CN bonds, the more polar it is. And polarity decreases the more carbons you have. So the longer the carbon chain, the less polar it is. Because carbon chains tend to be nonpolar, and the longer carbon chain you have, the larger percentage of the molecule is nonpolar. Does that make sense? So, So, why is polarity important? Like dissolves like. Things that are polar dissolve in other things that are polar, or non-polar things require non-polar things to dissolve. Like, you know that gooey, gross stuff that just doesn't come off? Like, that you need the glugon for? Because the glugon tends to be non-polar. And because it's non-polar, it can dissolve that gooey, wax, gross stuff that gets stuck on things. Or if you have gum stuck in a little kid's hair, you can, spray some of that on and get it off. It also, polarity also determines, intermolecular forces really determine a lot of other properties of substances as well. So hydrophobic, water hating or water fearing, nonpolar, hydrophilic, water loving. This is just kind of a quick chart to comparing. If you want to take a quick picture of this, it's worthwhile because it details the strength of the intermolecular forces, what they're present in, and the different types of intermolecular forces. London dispersion, dipole-dipole, hydrogen bonding, ion dipole.
And we have these in our email as well, right?
Yes, I did. I think I emailed you a copy of this PowerPoint, so you can always grab that as well.
You
Yes.
mentioned the glugon. Does that mean that, like, is soap, like, because it's an emulsifying agent? So
Yeah.
is that like...
And that's interesting. So what soap is actually a ionic substance, but with really, so if you take fatty acids, okay? Fatty acids are really long carbon chains with a carboxylic acid at the end of it. But if you react them with a really strong base, what it does is it neutralizes the acid and turns it into an ionic salt. But because that ionic salt has such a long carbon chain attached to it, it ends up being able to, it has a very significant nonpolar component. Because of the ionic part of it, it can still dissolve in water. Because of the long carbon chain, it can dissolve grease and oils and things like that and pull them into the water. So that's the useful thing about soaps. It can dissolve in water and can help nonpolar things also get pulled into the water and dissolve as well. Alright, so I wanted to discuss real briefly with our last few minutes different properties affected by intermolecular forces. So, viscosity, surface tension, specific heat, boiling point, and vapor pressure. So viscosity is resistance to flow. And so essentially things that slow very slowly, like molasses or honey, those are things with high viscosity, and things that flow very quickly, like water or gasoline, have very low viscosity, very low resistance to flow. So the intermolecular forces and the shape of molecules are really the biggest factors here. The greater intermolecular forces, and the more, I guess you could say, long the shape of the molecule is, the more the molecules can get tangled up with each other. Essentially, the more that, or the larger the viscosity is going to be. Yeah. So, a little stronger intermolecular forces, higher viscosity. Longer the molecules, higher viscosity. Then there's surface tension. So the surface tension is defined as the energy required to increase the surface area of a liquid. In other words, how much force do you have to apply to break the surface of a liquid, to get the molecules to separate? This is why bugs can walk on water, because the water molecules are pulled so tightly close to each other, they have such great attraction for each other, that it actually takes a lot of force to separate them. Has anybody ever done a belly flop? Okay. A belly flop is kind of like if you're diving for the first time and you're not used to diving, you're like gonna dive headfirst into the water, and then you're like, oh shoot, I don't want to dive headfirst, and you kind of pull back a little bit, and then you end up flat like this, and you go slap flat against the water. It really hurts. It really hurts because essentially you are maximizing the force needed to break the surface of the water. Whereas if you had a knife or if you just point your toes like a knife, or you point your hands like this into the water, the force, you cut the surface of the water with your fingers, and then, since it's already cut, then you can slide into the water easily, and it doesn't hurt at all. But yeah, surface tension is proportional to the intermolecular forces. The greater the intermolecular forces, the higher the surface tension.
So cornstarch have more intermolecular forces. More than water. The cornstarch, when you mix it with water, is like.
Cornstarch is really, really thick. Yeah, it's kind of it's a solution. I know what you're talking about. And also honey would have greater surface tension even than water, right? So, but yeah. The specific heat. Now this is interesting. The greater the intermolecular forces of a substance, the higher the specific heat is going to be. This is why water has such an incredibly high specific heat. The different molecules of water are really tough to separate. They have really strong attraction for each other. So specific heat can be think of as the amount of energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. But basically, it can also be thought of as the ability of a substance to store heat. Now, because it takes so much heat to get water molecules separated from one another, water can store a lot of heat. So, the reason why something like gold would have a much lower specific heat is because all of the atoms of gold, it's because it's a metal, and metals are good conductors of heat because the nuclei are not particularly bonded, but the electrons can move so freely that it allows for heat to kind of spread out throughout the entire thing fairly quickly. But if let's say you compared water to some other substance, like say, for example, PCl3, or even gasoline or something, water is going to have a much higher specific heat. And once again, stronger intermolecular forces, higher specific heat. Vapor pressure, it's the inverse. The greater the intermolecular forces, the lower the vapor pressure. Because essentially, vapor pressure is essentially what the pressure of the vapor will be when it comes into equilibrium with standing water. So essentially, higher energy molecules vaporize and they start bouncing around in there, and what happens is there reaches a sort of equilibrium, a maximum amount of vapor that can be spread about in the air, because what happens is the molecules get captured by the liquid, the gas molecules get captured by the liquid, but then high energy molecules from the liquid go back into the gas phase, and they're kind of going back and forth. Now, the stronger the intermolecular forces, those, like for example in water, those other water molecules are holding onto each other so tightly it's really difficult for them to break free and fly out into the atmosphere. That's why if you have a glass of water sitting out for a really long time, it doesn't evaporate very quickly. It takes a really long time. Whereas if you had a cup of gasoline, it would be gone in a few hours, right? That evaporates very quickly. Stronger intermolecular forces, the lower the vapor pressure is going to be. So, like I said, when intermolecular forces are stronger, more difficult for liquid molecules to separate from one another and escape to the gaseous state. And gas molecules are more attracted to one another and condense more easily. They're also more attracted to the liquid. And that's basically what I just said about it. Okay. And then last but not least, boiling point. Temperature at which substance goes from a liquid state to a gaseous state. So this is very much related to vapor pressure. Because the boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. And remember, stronger intermolecular forces equals lower vapor pressure, right? So if you increase the temperature, the higher the temperature, the faster the molecules are moving, and eventually they'll fly apart. Eventually they'll boil. However, if a molecule has strong intermolecular forces, you have to add a lot more heat to get those molecules to separate, right? But if it's weak intermolecular forces, you barely have to add any heat, and they'll begin separating immediately.
So like if you pull a vacuum on the liquid, it starts to boil.
Exactly, and that has to do with vapor pressure equaling atmospheric pressure. If the external pressure is low, like when you run a vacuum, then it'll boil at a much lower temperature. In fact, you can have water boil from the heat of your hand if you have a sufficiently evacuated chamber, if there's low enough pressure. Also, where it's have low pressure, like at the top of Mount Everest, water boils at like 60, 70 degrees because there's so much less pressure up there. All right, cool. Well, we'll probably stop there because we've gone a little bit beyond. But any questions before I go? So what do you think? Was that helpful?
Yes.
Okay, cool. I'll try to be having one of these every single week, and hopefully, I also rely on feedback. So if you have any suggestions for things that I can do to make sessions better, just let me know. You can either send me an email or whatever. And I am going to try and potentially do some live streaming of these. So if you're not able to come in person, you can actually, watch it at home or wherever. But I still haven't figured out the technology to that. And I'm kind of a dinosaur, so I need a little time.
Will it be at the same time, or will it change?
This time I just had to kind of schedule it wherever I could fit it, but I'm going to be reviewing the workshop time surveys that I went ahead and sent out to all y'all. I'll try to match the times that both work the best for everybody. But yeah, if this is a time that works for a lot of people, I'll probably keep doing it at this time. I also might try some other times in addition. I may have more than one session depending upon demand and such. Well, thank you for coming.
Thank you.
Do you guys also offer supplemental